questions and about once again the rotation, and those will be related with one second. Okay. And more or less we are going to solve directly or indirectly the rotational motion questions. So in the first question, it states that a bowling ball is projected along a smooth horizontal alley with the initial speed of v0. At first it slides without rolling, but the frictional force gradually causes it to start rolling. Determine the speed of the ball at the instant it begins to roll without slipping and show that this speed is 5 v0 upon 7. So in this case, first it is, we can say, it slides and there is no rolling motion, and after that there is a pure rolling and there is no sliding motion. So this is the basic question. So in this case we are going to use the friction impulse concept, or sometimes it is also called as a frictional force over the slipping time. So that is going to help to solve this particular problem. So we assume that the ball is having a mass m, ball have a mass m, and we also assume that its radius is capital R, and its moment of inertia is our I. Okay. And it is given that the ball is having an initial speed of v0. Therefore we can say that our initial speed, that is at v of 0, is equal to our v0, and during this time there is only sliding motion is there, so there is no rolling. Therefore we can say that our angular velocity at time t is equal to 0 will be equal to 0. And it is given that it is, so with respect to friction, we can say that while it is sliding, only the kinetic friction is going to act until the rolling without slipping condition is met. So we can say that while the ball slides, kinetic friction acts until rolling without slipping condition, rolling without slipping condition is reached, and that condition is our v is equal to omega times r. Okay. Until this condition is met, only the kinetic friction is going to take place. and therefore we are going to use the friction impulse. Okay. So let us consider that we have a friction impulse, and that friction impulse is denoted as J. Therefore we can say, and this impulse is going to affect the linear motion as well as our angular motion also. So therefore we can say the linear impulse and linear impulse, we are going to get this as m multiplied by v of f is equal to our mv naught minus j. Okay. And a vf is our final velocity, which we are going to calculate also. And next is our angular impulse. And so in case of angular impulse, we can say that the friction is going to produce the torque, and that torque can be represented as J multiplied by R. So we have angular impulse, and we can also say that the friction produces a torque, and the value of that torque will be equal to J multiplied by our R, and this will be giving us I multiplied by omega f is equal to J times R. Okay. And at this particular moment, we can say that the rolling without slipping is going to start. Okay. So we can say at the moment rolling without slipping begins. Therefore we can write its condition that our final angular velocity will be equal to final linear velocity divided by our radius. And therefore we can write that our J impulse is equal to I omega f upon R, and we substitute our omega f. So we get this as I vf upon R square, and we substitute this impulse. Let us call this equation number 1. So we can say from equation 1 we get this as our mvf is equal to mv watt minus, we have this as I upon R square times vf. And now we can combine the CVF. So we get this as vf will be equal to m plus I upon R square is equal to m times v naught. And we have this solid ball, which is a kind of sphere, and its moment of inertia is equal to 2 by 5 mr square. So we substitute value of moment of inertia, we get this as v of f is equal to m plus 1 upon R square, and this is our 2 by 5 mr square is equal to m times v naught. Okay. And here we can cancel out this m throughout, and R square also goes with R square. So we get this as v of f is equal to 1 plus 2 upon 5 is equal to v naught. So therefore we get our Vf is equal to 5/7 times V naught. Okay. So this is our velocity that was okay. In terms of figure, if we try to understand, we can just draw the approximate figure. If you are not able to follow, then the figure might little bit be helpful. Suppose this is the entire path, and somewhere here the frictional force kicks in. Okay. And here the velocity is our Vf at this particular moment, and initially it is only moving with the velocity of V naught. Okay. And its angular velocity, which is our omega naught, is equal to 0. Okay. And as soon as the friction is able to balance the, you can say, the rolling condition without slipping, it is going to roll from here, and like we said, there will be a omega f, and the Vf will be its velocity. So this is the basic, and here the impulse friction is going to starts. Okay, and this is the basic, you can say, approximation of the given question. Next question. It states that a cylinder of radius r spins about its symmetry axis with the initial angular speed omega naught. The cylinder is then gently placed on a horizontal table. It initially skids, but because of the friction, it eventually begins to roll without slipping. Find the final angular speed omega f of the cylinder when it rolls without slipping. So for this we can just draw an approximate figure. So we have a cylinder. So let us suppose this is a cylinder, and it is having a angular speed of omega naught. And suppose this is the horizontal table, and we place this on this horizontal table. And in this case, it says that because of the friction, it is going to roll without slipping. So let us assume that its frequency is our omega, and the frictional force is our F. Okay. And this is the basic figure of this. And in case we have to remember that the frictional force, that is our F, it causes the translational speed, that is our V, and to increase, and the angular speed to decrease, so that the pure rolling condition is met. That is our V is equal to omega times our R. That condition met, then only the rolling without slipping is going to take place. So here same concept we are going to use about the impulse, but in this case we have to remember that as soon as this cylinder is kept on the table, and this is our point of contact, let us suppose our P, and for the short duration of skidding is going to take place, but that is going to happen for the fraction of time, and for that we can assume that the angular momentum about the point of contact is conserved. Okay. And so we have to remember that our angular momentum angular momentum about point of contact which is our P is conserved during short skidding, or we can say impulse. And so let's find out what will be the initial angular momentum. So you can say angular momentum about point of contact immediately after placing the cylinder. And in this case, because before the cylinder is placed, it is only having the angular velocity. There is no linear velocity, or we can say there is no velocity of the center of mass. Therefore, we can say that our initial state our velocity of center of mass will be equal to our 0, and we can write that our L initial will be equal to I times omega naught. And now we come to our pure rolling, that is our final state. So you can say after it reaches pure rolling, which we are going to call as our final state, the velocity of the center of mass will be equal to its angular speed times r, and we can find out our angular momentum about the point of contact. Angular momentum about point of contact, and that angular momentum, let us call this as L final, and this L final will be equal to, let me draw the figure here, and this is our sphere, and we know that the angular momentum about its center, that is axis, let us call this as ICM, but we are supposed to find out angular momentum about this point P. Okay. So for that we are going to use the parallel axis theorem. Okay. So we can say that our L final will be equal to I times W omega plus, and this comes as a M, and we have over this as VCM times R. Okay, so this is our final angular momentum. And so in this case, there is no need to use the parallaxy theorem, because ultimately we are, one second, yeah, so there is no need to use the parallaxy theorem. Okay, so my mistake for that. Okay, and so we get that our final angular momentum is our I times omega f, and this comes as our m times VCM into r. Okay, so let's substitute the values, and we can write that our L final will be equal to, this comes as our I times omega f, and we have this as m. VCM we already know, VCM is our omega f times r. Okay, and times r, and so we get, this is our L final will be equal to omega f, we can take as common, and we have I plus, this comes as mr square. And now we can use conservation of angular momentum. Okay, so we can say conservation of angular momentum, and that conservation of angular momentum is going to give us L initial is equal to L final. So we can say our L initial is equal to L final. So we get I times omega naught is equal to omega f I plus mr square. Okay, so here we indirectly used our parallaxy theorem. Okay, and this is our with respect to the center, and this is our mr square. Okay, I missed that point. So indirectly we have used this by converting, by using the standard relationship, but ultimately we got the same result. I is about its center and mr is with respect to the point of contact. So this was correct part. And now we come to our omega f. So from here we can say that our omega f is equal to, we have this as I times omega naught and I plus mr square, and we substitute value of I, we have this as our half m r square, half m r square plus mr square times omega naught, and mr square we can just cancel out throughout, and this will be coming as 2 as LCM. So 2 and 3, so this will be 1 by 3 times omega naught. So we get our omega f is equal to omega naught by 3. So next question. It states that two solid rubber wheels treated at disc are mounted on the frictional pivots. The first wheel has a radius r, mass m, and initial angular speed omega naught. The second wheel has a radius small r, mass small m, and initially at rest. The wheels are gently brought into contact so that their rims touch. They skid briefly and then reach rolling without slipping at the contact. Find the final angular speed omega f of the first wheel. So in this case, there are now two wheels, and out of which only one is rolling and other one is stationary. So let us draw the initial figure. So let us suppose this is our wheel A. It is rolling with the speed of omega naught, and its radius is given as capital R and mass is capital M. And we have another wheel which is having a radius of small r, and let us call this as B, and mass is small m. Okay, so initially it is at rest. Now when they are brought contact with each other, and so this is our A wheel, and once again its mass is as usual and radius is our r, and this is our wheel B. I'm going to make a little bit distance between them. Okay, and this is our wheel B. Radius is small r and mass is small m, and suppose this is the point of contact of the wheels. So as soon as they are touched, so there will be, you can say, because of the frictional impulse or friction, there will be a force that will be applied on both the wheels. And initially A was rotating towards our left side, so it will be continue to rotate in this direction, but B will be start to rotate also in the other direction, and therefore we can say that there will be a frictional force on B that will be acting in this direction, and there will be a frictional force on our A which will be acting in opposite direction, that is our F. So this is the basic how it is going to behave when they are in contact with each other. Okay. So in this case, let us assume that they are having I1, I2 are the moment of inertia about their axis, and angular speed. Okay, so let us consider that we have our initial angular speeds, and first is our A, and for A let us call this as omega AI, which is our omega naught, and we have our omega B, and we have our B, and for B we call this as omega BI, and that is equal to 0. And we have our final angular speed, speeds, and we have our A, and for A let us call this as omega AF, and we assume that is equal to omega F, and we have our B, and that is our omega B final, and let us assume that is equal to our omega F2 and omega FB. And once again, there we are going to use the concept of the impulse, and you can say during the contact, the frictional force is going to produce an equal and opposite tangential impulses, which we had denoted as F and F, okay, on the two sides. Once again, we are going to consider the linear impulse, and then we come to the integral part, or we can say angular impulse. So we can say that during contact, the frictional force and this frictional force, we can write this as F of t, because it will be time dependent for how much duration this contact is there, and frictional force produces equal and opposite tangential impulses. On the two rims. And therefore, we can say the linear impulse which is our J will be equal to integral of our F of t times dt, and the angular impulse or we can also call this a integral of torque on wheel A and that will be equal to over minus of r times j, okay, because it is going to reduce the speed of the wheel, because this impulse is opposite to the our, and we have assumed that this is our omega f, and for B we have assumed this is our omega FB. So this impulse is acting in opposite direction to the our angular speed, so therefore it is going to reduce it or slow the speed, and we can write the equation that our moment of inertia of our A will be equal to final minus initial is equal to minus r times j. And similarly, we can write for our wheel B, we can say angular impulse on wheel B, and that will be equal to our plus small r times j, and it is going to increase the speed, or it is going to provide the necessary angular speed, not the speed. And therefore we can write this as our I of B will be equal to omega FB minus 0 is equal to r times j. And from here we can write the value of j is equal to, we get this as our I of B omega FB times divided by small r. And we substitute this j in our this equation. Let us call this as equation number 1. So we can say from equation 1 we can write this as our I of a omega f omega naught and minus r, and this comes as our I of b omega fb divided by small r. And once it is, you can say the rims touch and they roll without slipping, therefore we can say that tangential velocity at the contact point will be equal and opposite. So we can say that no slipping condition that is pure rolling therefore from here we can say that tangential velocities at point of contact are equal and opposite, or we can say that our tangential velocity, let us call this as a VA, will be equal to minus of our VB. So we can write this as omega f times r is equal to minus omega fb times small r, and from here we can find out our omega fb is equal to minus r upon small r times omega f. And we substitute it in terms of, let us call this as equation number 2. So we can say from equation 2 we get this as I of a is equal to omega f minus omega naught is equal to, and we have this as minus, this is our r IB upon small r and minus r upon small r times omega f. So we get this as our I of a is equal to omega f omega naught minus minus will be plus, and we get this as our I of b times r square upon small r square multiplied by omega f. And we can rearrange this particular equation and we can combine our terms of omega this omega f. So we get this as our omega f will